We're going to do a lab activity on Tuesday, and in that lab activity, we're going to plot a position versus time graph of an object moving at a constant velocity. Today and Monday, we're going to spend a little bit of time going over position time graphs so you know how to plot those graphs and how to analyze those graphs. The first thing I'm going to do before we do anything with calculations or determinations of velocities or accelerations or anything like that is just identify what different shapes of graphs represent. Clearly, a different shape of a graph will represent a different activity or something different going on than some other shape of the graph. We see 5 of them up on the board here right now. They all represent something different. They all mean something different. I want you, as we're going through this, to make sure that you understand why a certain shape means a certain thing. We have this habit, especially in Science 10 probably, we have this habit of maybe remembering a certain shape. Even in Physics 20, sometimes we remember a certain shape. It's important going forward that we can figure out, based on a shape, what a particular graph means. Here's the first one. It's a straight line on a position time graph. By the way, let me mention a couple things before we get into that shape. These graphs are all titled position time graphs because every graph, remember this, every graph forever and ever and ever, amen, for every graph is going to be titled y-axis versus x-axis. The y-axis will be listed first. You're going to do an activity on Tuesday. You're going to have to plot a position versus time graph on Google Sheets. When you type in that title, make sure that your title is whatever's on your y-axis versus whatever's on your x-axis. In that case, it'll be position versus time. Position dash time or position versus time. Now, the other thing that I should mention before we go into those shapes is the x-axis of your graph. The x-axis of your graph is always the manipulated variable. Always. So whatever variable you identify as a manipulated variable, it goes on the x-axis, and then the y-axis would be the responding variable. Remember, the manipulated variable, there's only one of them. In any activity, there's only one of them, and it's the variable that you change. Whatever it is that causes something else to change. And that's something else that changes because of the manipulated variable. That's the responding variable. So this is a position time graph, or it's a y versus x graph, or you could even say responding versus manipulated, because the responding variable is always listed first. Think of it in all 3 ways, but when you do your labs or plot your graphs, make sure you title it like this. Whatever specifically the responding variable is, or y-axis is, versus whatever the x-axis is. Okay, that's the same for all 5 of these graphs. Now let's take a look at the specific shapes. First one, we got a position time graph that is a straight line. The fact that it's straight, the fact that the slope of this graph is not changing, tells us something is not changing. Like, think about that. The slope of this graph is not changing. It's not curving. It's not changing. So that must mean that something in the real world isn't changing. What do you think it is? No, the position is changing. Look, the position right here is something. The position right here is something bigger, right? So the position is changing. Yes, correct. It would be the speed or the velocity. In this case, because it's position, not distance, it would be velocity. But the speed wouldn't be changing either. Yeah, this one represents a constant velocity. A constant velocity. Now, another way to say constant velocity is uniform motion. Remember what velocity is? It's the rate of change of position. Like, this isn't a hard one to remember, right? But you don't have to remember it. You can figure it out. You can understand it, right? Velocity is the rate of change of position. Okay, so you got to know the slope of this relates to velocity, right? Because position and time Rate of change of position is velocity. Position in time gives me velocity. And because the slope isn't changing, well, then the velocity isn't changing. So it's a constant velocity or uniform velocity or uniform motion. What about the second one? Martin, I'm going to ask you this one. The second one is, yes, this one, the position isn't changing. Look, it's a straight line. Something's not changing. Okay? You could say, although I'd want you to be more specific, the velocity is not changing, because it isn't, is it? This is a constant velocity, but it's a constant velocity of, how fast is it moving? 0. It's probably easier to say the position's not changing, right, than to say a constant velocity of 0. Straight line, something's not changing. Well, the velocity's not changing, but the position isn't changing either here. So we'll say this is constant position, or you could, I suppose, say that it's just at rest. If I gave you a quiz on this and you said not moving, I'd take that, right? Like that's means the same thing. How about this next one? We got position versus time here. Oh man, it's straight line again. Straight line, the slope isn't changing. So something's not changing. What's not changing here? What is it? The velocity. Wait a second, it's the same as first one then? Constant velocity? Yeah, it is. It is, kind of, but we want to be a little bit more specific on this one. This is a constant velocity or uniform motion, but specifically it's a constant. No, you can't have a, think about that. You can't have a constant decrease, because if it's constant, it's not decreasing, right? It's a constant velocity, but it's a constant negative velocity. Now, be careful with your wording and your understanding of that. That doesn't mean it's slowing down. Constant negative velocity doesn't mean it's slowing down. It just means it's going backwards. Like, not literally, okay, I'm driving my car forward in the first one, and then I put it in reverse in the third one, right? Backwards just means the negative direction. If I drive to Calgary and north is positive, if I drive to Calgary at a constant velocity, then I would represent that with my first graph. But if I turn around and come back, okay, I'm going in the negative direction, we could represent that by the third graph. I don't literally have to come back from Calgary in reverse in my car. I'm just going in the reverse direction. Does that make sense? The negative direction at a constant speed. Okay, the fourth one and the fifth one, those are curved. So that means that something's not constant. What's not constant? Well, the velocity, right? Position time, velocity is not constant. So what's happening? Something similar in 4 and 5, but not quite the same thing. Yeah. Acceleration. Yeah, this is a positive acceleration. And a positive acceleration means that the object is what? Speeding up. Yeah, it's accelerating, speeding up. What do you think the last one is? What's this last one? You got this. That's a negative acceleration, right? Which means what? It's deceleration. It's slowing down. Let me write that in too here. In brackets, speeding up. In brackets, slowing down. Now, the activity that you guys do on Tuesday is going to be pretty much this. Not perfect, constant positive velocity, but it's going to be very, very close. Close enough that we can represent it as a nice straight line sloping upwards like this first one. And then we'll calculate the slope of that, which is going to represent the velocity of that. And we'll show you on Monday how we'll go about doing that. Before we pack it up for the day, though, and for the weekend, let me just draw in one more. See if you can get this one. Here's my position time graph. Not very straight, but my position time graph. Here's my line. What does that mean? What does that mean? Tricky one, isn't it? That's a tricky one. Yeah, it's impossible. It's a trick question, right? So you're changing your position. You're going from one place to another without any time going by? Like, is that possible? Not unless we have some kind of wormhole or something, right? That's not going to be possible. So you're not going to get this one on a test. What about this one? Position versus time again? This one's even better. What's going on there? Or you know what? Let's just do this. Let's curve it. What's going on here? I'm accelerating, right? Look, speeding up, speeding up, speeding up, speeding up, speeding up, and then what am I doing? Nope, not slowing down. What is it? Going back in time, right? I went forward in time, and then I'm going back in time, which, as far as we know, isn't possible either. All right, have a good weekend, guys, and we'll pick this up on Monday.